This is beautiful. It's like secret code. Look at that. It's just a wall of trig. Hey, in this video, we're going to cover the first two sections of chapter 1 of the second book. So, reciprocal trig functions, inverse trig functions. Not really a lot here. Little graphing, little algebra. So first we'll look at the reciprocal functions. So we have 3 of them. You've probably heard of them before. The first is cosecant, which is the reciprocal of sine. In the previous curriculum, they abbreviated cosecant as I am used to writing it, just CSC. Now the course guide uses cosec, and it appears like that in the formula book as well. So I don't know. That's what they're using now. Then we have secant, which is the reciprocal of cosine, and we have cotangent, which is the reciprocal of tangent. Therefore, it's equal to cosine divided by sine. Okay, and we should be able to evaluate reciprocal trig functions just like normal trig functions. So as an example here, if we want to know what cosecant of pi over 6 is, that just means it's 1 over sine of pi over 6, and I know that sine of pi over 6 is 1/2, so it's 1 divided by 1/2, or 2. You should be able to work out what the graphs of these 3 reciprocal functions look like because you know how reciprocal functions behave. So here's our sine graph. A reciprocal function is going to have vertical asymptotes at every 0, and it's going to have zeros at any vertical asymptotes. Sine doesn't have any vertical asymptotes. And then other than that, it's just going to have reciprocal y values. So it'll be above the x-axis wherever sine is, below the x-axis wherever sine is. Here's what cosecant looks like. All right, we should be able to work that out without too much difficulty. Notice, by the way, Desmos requires you to use CSC. If you try typing in cosec, it doesn't know what is that. So yeah, most software that I've dealt with uses CSC. I don't know why the IB has made this change. Anyway, we can do the same thing with cosine. Again, identify the zeros, so we should have vertical asymptotes there. Otherwise, just like sine and cosine are just the same 2 graphs but shifted over, same thing with secant and cosecant. Tangent is a little more exciting because we have zeros at the multiples of pi, which are going to become vertical asymptotes. We also have vertical asymptotes at the odd multiples of pi over 2, which are going to become zeros. So what should the graph of cotangent look like? Well, one idea that might come into your head is just to take the tangent graph and just shift it all over by pi over 2, and that's pretty close. But let's just focus in here between 0 and pi. So our cotangent function needs to, at 0, it should be a vertical asymptote, but then it should have all positive values since the tangent value is positive, until we get to pi over 2, where cotangent should be 0. And then to the right of pi over 2, it should be negative, and then it should be on its way to a vertical asymptote again. So it's actually going to look kind of like where my mouse is going there. So it's kind of like a reflection of tangent, and then shifted over a little bit. So the IB hasn't really asked too many questions, if any, about the graphs of the reciprocal functions, but I just wanted to point out, if you know what sine, cosine, and tangent look like, which you should, then you can work out what cosecant, secant, and cotangent look like. There's no need to really commit a lot of mental space to memorizing these, because you should be able to derive them in the event that you need them. And if you graph them all at the same time, it looks pretty. More importantly than the graphs is to be able to work algebraically. So anytime you have an equation that has a reciprocal function in it, just rewrite it so that it has your normal sine, cosine, tangent in it, and then solve it like you would have at the end of the previous book. So we get our trig function by itself here. And then we ask ourselves, well, what angle would we need to put in here in order to get root 3 over 3 out? That would be pi over 6. And then solve for x. And this is 5 pi over 24 is one answer for x. There was, a particular domain that we would answer on, so we'd have to consider other values, but no need to get into that right now. And that's all that there is to know about the reciprocal functions. Just, consider the normal ones and you're good to go. That brings us to section B, which is about the the inverse functions. And we talked a little bit about this back with just like right triangle trigonometry. So using inverse trigonometry to like figure out the angle if we knew some of the sides of a right triangle and such. But we can also consider it as a function with a graph and then start doing compositions with the inverse trig functions and the regular trig functions. So let's take a look at that. First thing, just the notation on the calculator, at least on the TI Nspire, they use this notation, which is, I don't know, what I tend to use. It's less writing. However, you can also use arcsine, usually abbreviated just arcsin, arccos, and arctan, means the exact same thing. And sometimes that's easier because then there's no risk of you accidentally mistaking this inverse notation as a reciprocal. I really can't emphasize this enough. Please be careful about your -1s. If you did want to use a -1 to indicate an exponent, then I put it outside of parentheses. If you put the -1 kind of in between the sign and the x, it absolutely means inverse. So please don't write the wrong thing and don't interpret something that you read incorrectly either. Now, since these are inverse functions, we can think about their graphs by considering well, what should happen to the graphs of the original functions if we reflect over the line y equals x. So first of all, the domains of the inverse functions should be pretty straightforward. The domain of arcsine is -1 to 1, same as arccos, and that's because the range of sine and cosine are both -1 to 1. And the domain of arctan is all real numbers because the range of tangent is all real numbers. The ranges of the inverse functions is where things get a little more tricky, because if we consider the entire graph of sine, cosine, or tangent, obviously they would not have an inverse function because they all fail the horizontal line test. So we need to restrict their domains, and we do it in the following way. So looking at the sine graph, we've decided to go from -π/2 to π/2 because that restricted domain on sine will correspond to every possible y value that sine puts out. It goes from -1 all the way to 1. Could we have decided to start at π/2 and then go all the way to 3π/2? Yeah, we could have, I guess, decided to do that, but this is what we've agreed upon. So the restricted domain of sine of x becomes -π/2 to +π/2, and that makes the range of arcsine -π/2 to π/2. Similarly, for cosine, we restrict the domain to be from 0 to pi, because that hits all of the y values from -1 to 1. Therefore, the range of arccosine is from 0 to pi. And then with tangent, we just restrict in between two vertical asymptotes. So we go from -π/2 to +π/2, and that becomes our range of arctan. And again, with past paper questions, you're not going to see a lot just asking specifically about the graphs themselves, but we do need to know these domain and ranges in order to do some algebraic questions involving the inverse functions. So we see that here. It is not just as simple as saying, oh, arcsine and sine cancel out. Sometimes they do, sometimes they don't. Let's take a look at this. So in this first example, sine of π/3. Okay, what is sine of π/3? Sine of π/3 is going to be √3/2. So now we're asking for the arcsine of √3/2. And that's fine. I'm allowed to take the arcsine of √3/2. It's going to be some value along in here, and when I go up to the arcsine graph, I'm going to get π/3 out, because of course π/3 is the angle whose sine value is √3/2. I should say it's the angle that is included in the domain of arcsine. See what I mean with this next example now. Arccos of -π/6. So what is the cosine of negative pi over 6. Well, that's also root 3 over 2. The problem is that when I take root 3 over 2 and I check my arc cosine curve, is I'm getting a positive value out. I'm not going to get negative pi over 6. Instead, I'm going to get the angle in the first quadrant that has a cosine value of root 3 over 2, and that's going to be positive pi over 6. So it's not just as simple as these two canceling out. We need to really consider what is the domain and range of the arc cosine or the arc function, whichever one it is. Let's take a look at this one here. So arc tan of 0.3. Well, I don't really know off the top of my head what angle that should be, but it's going to be something in the first quadrant, and that's fine. When I take the tangent of the thing in the first quadrant, I still am going to get 0.3 out. So that works, and we see we're going to get the same answer out here for this letter D. Arc cos of negative 1/2. So that's going to give me the angle in the second quadrant, whose cosine value is negative 1 over 2. And again, I know it's in the second quadrant because when I put in a negative x value, and then I check my arc cosine curve, all the y values here are between pi over 2 and pi. So that's in the second quadrant. And then when I take the, that angle is going to be 2 pi over 3. And when I take the cosine of 2 pi over 3, I'm going to get negative 1/2. And for the final two, tangent of pi is equal to 0. What is arctan of 0? Well, it's still 0. It goes to the origin, so that's not a problem. And then for this one here, sine of 4 pi over 3, that's in quadrant 3. So that's going to be negative, negative root 3 over 2. But when I ask arc sine for the angle whose sine value is negative root 3 over 2, arc sine can only give me an answer that's on either the first quadrant or the fourth quadrant. So it's going to give me the angle of negative pi over 3. All right, so it's a little tricky, so like make sure to like think about this. Don't just breeze through it. Make sure that it makes sense. We can also solve equations with the inverse functions. These can be a little weirder even. So let's look at this one. Arctan of x equals pi over 3. So you want to think about this as x equals tangent of pi over 3. Is that doable? Yeah. Tangent of pi over 3 is going to be square root 3, and that's definitely allowed. That's in the pi over 3 is within the range for arctan. So we can solve this. For letter B, 2 pi over 3, that's also within the range for arc cosine. So we're really solving x minus 1 equals the cosine of 2 pi over 3. So x minus 1 is equal to negative 1/2. So we're adding 1, and then x should be equal to 1/2. For this third one, however, yeah, we could solve x equals sine of 2 pi over 3. The problem is that 2 pi over 3 is not part of the range of arc sine. So strictly speaking, this equation actually has no solution. If we look back at the graph and we tried to solve this red function, set it equal to 2 pi over 3, it doesn't work because it does not go high enough up. There will be no intersection. So that's all that I would really have to say about this. As I mentioned in previous years, it wasn't really a major focus for the IB, so I do not anticipate it being one moving forward, but as always, I could be totally wrong. Again, the graphs, we shouldn't need to memorize too much there because we should be able to figure out what their graphs look like of the reciprocal and inverse functions just using information that we already know. And the algebra is where we just want to like take things a little slowly, be mindful of what we're doing, think about what the question actually means, so that we don't make some horrible mistake. And anyway, the last thing I wanted to show you is just on the calculator, they all are in the same spot. So you got your 3 regular trig functions, we got our reciprocals here, we've got our inverses here, and you know what? You've even got the inverses of the reciprocals, although That's not anything that I've ever had to use. Never used these three buttons in my life. So there you go. That's fun. I'll leave you here. No special meaning. Just a quotation that spoke to me. Catch you next time.